Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will be discussing equations of motion. Equations of motion. Now, we will first discuss the case of constant forces. Then we will discuss non-constant forces as well. So we know when we study dynamics and kinematics or mechanics overall, our ultimate goal is to describe how a particle will move when it is acted on by a set of forces, right? So there is some particle having certain mass. Now it is acted upon by different forces, F1, F2, F3, for example. There can be many. So our goal is to describe its motion. To describe its motion means our goal is to find somehow its position at all times and its velocity at all times. I repeat, in the study of mechanics, which includes dynamics and kinematics, our goal is to describe how a particle will move when it is acted on by a set of forces. So if we have some particle having certain mass m, it may be acted on by many forces. We have shown here 3 forces. Now, to describe its motion means we need to find or we need to predict its position at all times and velocity at all times. So we will be talking in case of one dimension, which is easy for you to understand. Now, ideas can be generalized to 2 and 3 dimensions. Now in position, in one dimension, position we represent by x. So we need to find x of t, the function which gives the position of the particle at all times, position time function. Similarly, we need to find v of t, where v is the velocity of the particle and v of t is that function which gives us the velocity of the particle under consideration at all times. Now these equations, the equations by which we make prediction of the position at all times and velocity at all times, these equations are called equations of motion, right? So schematically, the analysis in one dimension can be represented as, we know all forces. So all forces which are represented by sigma F, all forces are known. From that, we find using Newton's law acceleration. From that, we find x of t and v of t, right? Now, acceleration we obtain from the all forces acting on the body using Newton's laws. As we have done certain applications of Newton's laws of motion. Once we know the acceleration of the body, next step is the mathematical one of finding the position and velocity at all times That is, next step is to find these two functions from acceleration and initial position and initial velocity. Initial position and initial velocity. Initial position means velocity at t is initial position means position at t is equal to 0, and initial velocity means the velocity of the particle at t is equal to 0. I repeat, how we obtain equations of motion. We figure out all the forces acting on the particle. Using Newton's second law, we find the acceleration of the particle, or using Newton's laws of motion, we find the acceleration of the particle. Once we know the acceleration, then using mathematics, we make prediction about position at all times. That means we figure out the position time function and velocity time function. But for this to do, to complete this process of finding x of t and v of t, we must know the initial position and initial velocity, right? Now, if the force is constant, then our acceleration is constant. And for constant acceleration, the solutions of x of t and v of t are easy. We will do it now, how to obtain that. So we are taking first forces constant. So we assume that we have found acceleration from Newton's laws. Now we want to find v of t and x of t. Let me make it clear. So v of t we want to find and x of t we want to find. A we have obtained from Newton's laws of motion. Now, how to find v of t and x of t in case of constant forces, where acceleration is constant, right? So we know acceleration is time derivative of velocity, right? A is dv by dt. So I can write dv equal a dt, right? Then I integrate my left hand side and right hand side and give limits on left side from v0 to v, and on right hand side 0 to t. That means v0 is initial velocity, that is velocity of the body under consideration at t equal to 0. V is velocity at time t, so future time t, right? Then my left hand side will simply become integral dv is v. Then I put the limits, upper limit minus lower limit. So my left hand side will become v minus v0. Now since I am saying force is assumed to be constant, so acceleration is constant. So it is not changing with respect to time. So I can take it outside the integral. Then I have 0 to t dt, which is just t. So it is simply at. So we got the relation v is equal to v0 plus, so v minus v0. Then I take v0 to the right hand side. So v is equal to v0 plus at. Or sometimes we write v of t because it is function of time is equal to v naught plus at. This is my velocity time function. Let me encircle it. So this is my velocity time function. From this equation, if I know initial velocity v naught, I can find or predict velocity at any future time t, provided the acceleration is constant. Now we obtain the position time function. So next step is to find the position time function. So we start this way. We say velocity is time derivative of position. V is dx by dt. So I can write dx is v dt. Then I substitute for v using first. I can write v naught plus at. Right? I replace v by v naught plus at. This is my first. So using first. Then I write it v naught dt plus v naught t dt. Sorry, not v naught. V naught dt plus at dt. Right? So integrating, this is dx from x naught to x. Here my variable integration is time. So I write t is equal to 0 to t v naught dt plus t is equal to 0 to t at dt. Right? That means x naught is initial position, which is position of the body, position at t is equal to 0, and x is position at time t. So change the color first. So my left side hand side will simply become x minus x naught. It is elementary calculus, you know it. This v naught is out of the integral, 0 to t dt, because v naught is not going to change with time. A is also constant with respect to time. So it is 0 to t a, sorry, not a. A I have taken outside the integral. It is t dt, right? So it is just v naught t. It is a, and integration of t dt is what? T square by 2. Write it half t square. Right? What is the equation? My equation is x is x naught plus v naught t plus half a t square. X is x naught plus v naught t plus half a t square. Or we write it x of t because it is actually a function, position of function of time, x naught plus v naught t plus half a t square. So I name this equation. This equation is my second equation. This was my first equation. So these two equations are equations of motion for a particular body moving in one dimension under the action of a constant force, because we have assumed the force is constant and therefore acceleration is also constant. Now, if the acceleration is not constant, the integrals which were appearing in these equations, these integrals are more complicated to evaluate, right? And one more thing, when we solve these integrals this way, using this mathematics which we have done, and we find the explicit functions of velocity and position, this approach is called analytical approach. There's another approach to solve the problem, which is called a numerical method, in which we use our computers to evaluate the integrals, but not to obtain the functions v of t and x of t, but instead the numerical values of v and x at any time t. I repeat, in numerical method, we use computer to evaluate the integral, and then we find the numerical values of velocity and position at any time t, right? But there can be forces which depend on different variables like time, velocity, and position. In those cases, you cannot treat acceleration as constant, and these equations are not valid. I give some examples. Examples of non-constant forces. First example I give for force depending on time. Force depending on time. When we analyze the braking of an automobile, normally we assume acceleration to be constant. But in practice, the acceleration in case of braking is not constant. Because what we do when we brake an automobile, especially at high speed, we usually apply the brake slowly at first and then more strongly as the car slows. I repeat, in practice, what we do when we brake a vehicle or car, especially at high speed, we usually apply the brake slowly at the first and then more strongly as the car slows. Therefore, the braking force depends on time during the interval over which car is slowing. So the function a of t in braking of an automobile, the function a of t, that is acceleration time function, will depend on the details of how we apply the brakes. So this force which we apply to stop a vehicle at high speed certainly depends on time over which we apply that force. Second example we take for the force depending on velocity. There is a force called drag force. What is drag force? You must be knowing. I'm just reminding you. This drag force is a velocity dependent force. Now first, what is drag force? It is the force experienced by a body moving through a fluid medium such as air or water. This frictional force is called air drag also, or in general drag force. This is a kind of friction. This frictional force or drag force increases with velocity. You may have encountered this effect when you try to walk in a swimming pool. If you walk slowly, you feel only a small resistive force. But if you try to walk quickly, the resistive forces on your legs can be quite large. The faster you try to move, the greater is the drag force. This is the example of a force which depends on velocity. So certainly acceleration can't be constant because force is velocity dependent. Third example we take the example of the force depending on the position. Force can depend on position. For example, if you attach a spring to some mass m, if the spring is at its natural length, that means spring is neither stretched and nor compressed. That is the meaning of natural length. The spring will not exert any force on this mass m, but if you stretch it, for example, if I stretch it this way, then force on this mass due to the spring will be to the left, right? And if I compress this spring like this, then force on this mass will be this way. You know, all springs are characterized by a constant called force constant, represented by K. So is a force, K is a force constant or spring constant. The force exerted by the spring is written as minus Kx, where x is the change in length of the spring. Negative indicates that it is oppositely directed to the displacement. If you move mass to the right, force is leftward. If you move mass to the left, force is rightward. So it is oppositely directed to the displacement. Here you can see, if you stretch this spring by a larger extent, the length of the spring will change to a greater extent compared to its natural length, so force will be greater. And same is case in case of compression. If you compress the spring to a greater extent, force will be greater. So this force depends on the amount of stretching or compression of the spring, and in other words, it depends on the position of the particle which is attached to it. So this force acting on this mass m is position dependent. So acceleration is not constant here also. So in these situations, we cannot use the equations 1 and 2 which we have obtained for constant forces. So next, I take the case of time-dependent forces. Time-dependent forces. Just an elementary introduction to the problem. Now we are talking of time-dependent forces, but which method? Analytical method. Analytical method. Now to make this thing clear to you, how we use analytical method to obtain equations of motion when the force depends on time. Now if force depends on time, then certainly acceleration depends on time. So how we proceed to find the equations of motion? We know a of t will be time derivative of velocity function as we have done it. So I can write dv is a of t dt. Then we integrate on the left side v naught to v. Here from 0 to t, what is understood here, I don't need to write it now. V naught is initial velocity, velocity of the body at t is equal to 0, v is the velocity at time t. So my left hand side will be simply v minus v naught. My right hand side, now you can understand what it will be. I cannot take this a outside, so I keep this integral as it is because I don't know how acceleration depends on time. Previously, we took this acceleration outside the integral because acceleration was constant. So I will keep it this way, 0 to t, a of t, dt. And I can write v of t is v naught plus 0 to t, a of t, dt. V naught plus 0 to t of t dt. So this is my velocity time function. One equation, and we name it 3, which can be used when the force is time dependent, that is acceleration is time dependent. Then we can obtain position time function also. This way we write velocity time function is time derivative of position. Then I can write dx as v of t dt, right? Then I integrate 0, not 0, x naught to x, 0 to t, now it is understood. X naught is initial position, that is position at t is equal to 0. X is position at time t. So it will become x minus x naught equal to 0 to t v of t dt, right? I keep it this way because I have not solved for v of t. It contains this unsolved integral. Then x of t is x naught plus 0 to t v of t dt. So this is my second equation, that is position time equation, which can be used in case of forces depending on time dependent forces. I name it equation 4. This is 3. This equation and this equation we can use in case of time dependent forces. Now I will demonstrate their use in a problem. So we will together solve a problem. I call it sample problem. This problem is like this. It says a car is moving at 105 kilometer per hour, which is, if you make the calculation, about 29.2 meter per second. 105 kilometer per hour, which is 29.2 meter per second, right? So the driver suddenly begins to apply the brakes, but does so with increasing force so that the deceleration increases with time. According to change the color here, A of t is equal to Ct, where C is minus 2.67 meter per second cube. Part A says how much time passes before the car comes to rest. Is another part of the problem. Part B, which says how far does it travel in the process. Repeat the question. A car is moving at 105 km per hour, which is 29.2 meter per second. The driver suddenly begins to apply the brakes, but does so with increasing force so that the deceleration increases with time. According to A of t is Ct, where C is minus 2.67 meter per second cube. Part A says how much time passes before the car comes to rest, and B says how far does it travel in the process. So you can understand this is braking force, which we have already discussed. It is a time-dependent force. That's why acceleration is time-dependent. This equation gives how acceleration depends on time. Acceleration is negative because you are stopping the car from some speed to rest. So it is the case of deceleration, negative acceleration. So we are asked in part A to find the time which passes from the moment braking force is applied to the moment car comes to rest. And during this process, we have to find the distance traveled by the car. So we do the solution. First, we take it to part A. So we need an expression for V of t so that we can find the time at which V is 0. So we use the equation which we have derived using v of t is equal to v naught plus 0 to t a of t dt, which we have this equation, because this is the case of time dependent force. We can use this equation. V of t is v naught plus integral 0 to t a of t dt, right? Now a of t is given to us. A of t is what? Ct. We substitute. We write it v naught plus 0 to t a of t, we write ct dt. Now c is constant, so it will turn out v naught plus, take c out and integrate in 0 to t dt, it will become simply half ct square. So my v of t is now v naught plus half ct square. Now setting v of t equals 0, because we have to find time at which time which passes before the car comes to rest. So final velocity I set to 0 and solve for t at which car comes to rest. I name that t1. Setting v of t to 0 and solving for the time t1 at which the car comes to rest, right? Oh my, change the color. So my left hand side is 0. Here is my initial velocity v naught. Then I have half c t1 square. When I solve for t1, it will be under root minus 2 v naught by c, right? Because when you take this v naught to left hand side, it will be minus v naught, then 2 will come upstairs, it will come to minus 2 v naught, then c will come down, then there will be a square root. Substitute the values. It is minus 2, and we have v naught which is given 29.2. we take in SI units, meter per second. Then you have c which is given minus 2.67 meter per second cube, minus 2 times 29.2 meter per second divided by minus 2.67 meter per second cube. This whole thing is within the square root. When you solve it, you can check it. It turns out to be 4.68 seconds. This marks the answer of part A. So 4.68 seconds. It takes 4.68 seconds to bring the car to rest. Now we move to part B. We are asked to find the distance traveled by the car during this process. So we need this expression. X of t is x naught plus 0 to t v of t dt. This one. Because this is valid for time dependent force. X of t is x naught integral 0 to t v of t dt. right? Now what is my V of t? My V of t is V0 plus half Ct square. This is my V0 t. This one. V0 plus half Ct square. I substitute. I write here V0 plus half Ct square dt to become x0 plus when you solve it, I write directly V0 t plus what? 1 by 6 Ct cube. Check it. X of t is now x0 plus V0 t plus 1 by 6 Ct cube. See how? First, this will split into two integrals. First will be V0 dt, and that will just give you V0 t. Then you have integral 0 to t half Ct square dt, half c you will take out. Then the integration of t square will be t cube by 3. When you multiply half c into t cube by 3, 3 2 will be 6, be 1 by 6 Ct cube, right? So you will have this expression. Now with t equal to t1, which is 4.68 seconds, is the time to stop the car. Distance traveled is given by x of t, setting x0 to 0. We assume the point where car begins to stop or braking force is applied. We take that our origin, taking x0 equal to 0. We have to solve for now x of t1, right? Which is plus V0 t. V0 is what? 29.2 meter per second. Substitute for time, which is 4.68 seconds. Then you have plus 1 by 6, and you have value of c minus 2.67 meter per second cube. Then you have t cube, that's 4.68 second whole cube. When you solve it, and check at your places and get x of t1 equal to 91 meter. So this is the distance traveled by the car before it stops. Check the numbers first. X of t is x0 plus V0 t plus 1 by 6 Ct cube. Then we substitute the values. 29.2 meter per second. Here we have 4.68 second plus 1 by 6 times minus 2.67 meter per second cube times 4.68 second cube equal to 91 meters. This is my answer. This sample problem we have done. I hope it will help you to understand how we use equations of motion to make predictions about the system or any body which is under question. Now I will give you some homework. Question 1. This is a simple question. It shows a figure. Question says, figure A, I will give you the figure, shows 3 crates with masses and 1 equaled 44.2 kg and 2 equaled 22.8 kg and M3 equaled 34.3 kg on a horizontal frictionless surface. Part A says, what horizontal force F is needed to push the crates to the right as 1 unit with an acceleration of 1.32 meter per second square. Part B says, find the force exerted by M2 on M3, and part C says by M1 on M2. This is the figure. So I have 3 blocks. Block 1 with mass M1, then block 2 with mass M2. No, sorry, these are crates, not blocks. Then I have another block with mass M3, where mass is M2. Let me make it clear first. Where is my eraser? Then I need my pen back. My pen. So first this M3. This is my M2. Now it is clean. Then this is force F, and this figure A. So I repeat the question. Figure A, M2, M3 shows 3 crates with masses M1 equal to 45.2 kg, M2 22.8 kg, and M3 34.3 kg on a horizontal frictionless surface. So there is no friction on the surface. Part A says what horizontal force F is needed to push the crates to the right as 1 unit with an acceleration of 1.32 meter per second square. Part B, find the force exerted by M2 on M3, C by M1 on M2. This is your question 1. In question 2, I'm finding a suitable question for you. Okay. This is a simple question. A rock is dropped from a 100-meter high cliff. How long does it take to fall? Part A, first 50 meter. And part B, the second 50 meter. Read the question. A rock is dropped from a 100-meter high cliff. How long does it take to fall? The first 50 meter and the second 50 meter. This is all for today. Do your homework, be sincere with your studies, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.